In today's video, we will be learning how to solve direction fields for Calculus 2. So let's start out with this equation here. Okay, so it says that y prime of t is equal to y times y plus 1 times 5 minus y. And the question wants us to find the equilibrium solutions. The conditions led to solutions that are increasing and are decreasing in time. And it wants us to graph the general direction field. So let's just start off with this equation. Okay. And I want you guys to think, what does this equation look like? Well, we know that y prime of t is just dy over dt, right? This is just dy over dt. And see how there's an equal sign here? This means that the first derivative is equal to this. Now, if you remember from Calculus 1, setting the first derivative to 0 will give you the slope at 0, where the slope is 0, and it also tells you the critical points for the function. So let's set it to 0. Let's take this y out. If we set it to 0, then y just equals 0. And we have y plus 1 equals 0, and 5 minus y equals 0. For this one, if we subtract 1 to both sides, we get y equals negative 1. And for this one, if we want to get y by itself, we can just do 5 minus 5 equals 0. And we know that's true. So that means that y equals 5. So now what we're going to do is, just by looking at this, we know that 0, negative 1, and 5 are critical points for the function. Now, from Calculus 1, if you remember, in order to figure out whether your critical points are increasing or decreasing in time, which is what B, this part of the question is, we have to set up intervals within those critical points. So just to mark, this is the solution for A, right? These are equilibrium solutions, y equals 0, negative 1, and 5. Now we're going to test intervals. So let's start with this negative 1 since it's the most negative point. Let's test what happens between negative infinity and negative 1. So we're going to test here. So using our first derivative equation, which is right here, let's just test negative 2, since that's in our interval. And let's see what happens when we have negative 2 times negative 2 plus 1 times 5 minus 2. So negative 2 times negative 2 plus 1, this is just negative 1, times, what is 5 minus 2? Negative times a negative is a positive, so it's really just what? 7, right? Now, negative times a negative is a positive, so that's going to give us 2 times 17, or not 17, sorry, 2 times 7. And that equals 14. Now, notice that the number is a positive number. So this means that the function is increasing in this interval. Now we need to test another interval, which will be from negative 1 to 0, because this point right here is our other endpoint, or our other critical point. Now we can test a value in this interval. If we test, let's just do 0.5. So we have negative 0.5. Actually, let me write this down here. Negative 0.5 times negative 0.5 plus 1 times 5 minus negative 0.5. So let's simplify this. Negative 0.5 can stay here, and negative 0.5 plus 1 is just 0.5. And then we have 5 minus 0.5, which would be 5.5. Now, if we know what, we don't even You can use a calculator to solve this, but if you just think about it, negative times a positive gives a negative, right? And then negative times this other positive is just going to give you another negative. So that means that this number is going to be negative, which means that it's decreasing. Okay. So now we can test another interval, which is going to be from 0 to 5, because those are our two critical points. There's from 0 to 5. So let's try from 0 to 5. Let's just test an easy number like 1. So if we plug 1 in, we'll get 1 times 1 plus 1 times 5 minus 1. 1 plus 1 is 2. So you have 1 times 2 times 4. This is going to give you 8, which tells you that the function is increasing along this interval. Now we can test our last endpoint, or sorry, critical point, by testing from 5 to infinity, because 5 is the most positive value that we have for our equilibrium solution, and then everything else is just going to infinity. So 5 to infinity. So let's do test 6, since that's within the interval. So what was our function? So we have 6 plus 1 times, let's do 5 minus 6. So 6 times 7, right, times negative 1. This is going to give us negative 42. That is decreasing, right? So now what we can do is we can set up a compound inequality that tells us where our function is increasing and decreasing. So the way that I would do this is to show whether we're increasing in time. Instead of using negative infinity, let's use a. Let's set a. And let's say that a is always going to be less than negative 1. Is that true for increasing in time? Well, let's look at this. Our interval is from negative infinity, right? I'm looking at this right here. From negative infinity to negative 1. So that means that it's always going to be increasing from a as long as it's less than negative 1. Okay, so I'll just denote this increasing in time. Now, there's another one that we have that's increasing in time, and it's from 0 to 5. So now we know that anything between 0 less than a less than 5 is also increasing. Now we want to find what's decreasing in time. Okay, so we know there's two intervals where it's decreasing. The first one we tested was from negative 1 to 0. So that means that anything from negative 1 is less than a is less than 0 is decreasing. And our final interval, which was from 5 to infinity, is also decreasing. So we can rewrite that as a so long that it's greater than 5. This is the answer for part B. Now we need part C. So part C wants us to graph a direction field. So I'm just going to set up, let's set up this XY thing, right? XY graph. And we can actually make it easier and just do this. So first, let's go back up to the top. In the top, we found we had 3 equilibrium solutions for part A right here, right? We had y equals 0, y equals negative 1, and y equals 5. That means that the slope is 0 at those 3 coordinates for y. So y equals 0. So this is just y equals 0, right? We just have this straight line that goes across. And then we had y equals negative 1 and y equals 5, where the slope is 0. So let's just do this and say this is y equals negative 1. And then what was it one? Y equals 5? Yep. So let's just say this is y equals 5. So so we have this interval, this, and this. And remember, we actually tested all of these to see which way we're moving in our direction, whether the slope is increasing or it's decreasing. So let's start with our first interval. We tested from negative infinity to negative 1, right here. So from negative infinity to negative 1, we knew the slope was increasing. So that means for all values less than negative 1, our slope was going up like this. So usually in a direction field, you have like these little lines that kind of just point which way the slope is moving. So it's going to look something like this because we're increasing in slope. Now we can look for this another little interval right here, all of this area, which is y equals negative 1 to 0. Well, we found that from y equals negative 1 to 0, our function was decreasing. So that means our slope is going down a little bit like this. So our arrows are now pointing down. Note that the arrows aren't actually the slope. It's just telling us what the slope is doing, whether it's increasing or decreasing. So now we can check from 0 to 5. We said the function was increasing, so we can point our arrows going up, right? These are our little direction fields, right? So the slope is not 0, but it is increasing. Now we test our last interval, which was from 5 to infinity. For all values of 5 to infinity, our direction was decreasing. So our field, the slope, will be going down, like that. Okay, so that is part C for our direction field. So hopefully that wasn't too difficult. Now let's set up one more equation. Let's set up y prime of t is equal to 12y minus 15. So we want to find the equilibrium solution and make another sketch of the graph and determine whether the equilibrium is stable or unstable. And I'll explain what that means. So let's just rewrite. We can remember this is just dy over dt, which tells me that this is the first derivative of the function. We know that setting the first derivative of the function equal to 0 will then give us the slope at 0, where that is. So 12y minus 15 is equal to 0. Adding 15 to both sides gives us this. Dividing by 12 gives us y equals 15 over 12, but we can simplify this and make this 5 over 4 because we can divide both sides by 3, or both the numerator and the denominator by 3. Now we have 5 over 4. This is our equilibrium solution. Okay, now this one only has 1, so it is also a critical point. Now we need to test 2 intervals instead of the 4. We need to test what's happening from infinity to 5 over 4, and we need to test what's happening from negative infinity, or not negative infinity, sorry. Let me rewrite this. We need to test what's happening from negative infinity to 5 over 4, and from 5 over 4 to infinity. So let's just rewrite these as tests. We want to see whether the function is increasing or it's decreasing along these intervals. So for this one, for this top part, the negative infinity 5 over 4, let's test 1, since that's within the interval range, since 5 over 4 is greater than 1. And let's put that into the equation. 12 times 1 minus 15. That's going to equal 12 minus 15, which is negative 3. That tells me that the function is decreasing within this interval because we get negative numbers, which also tells me that the slope is decreasing. Now we test from 5 over 4 to infinity. Let's test 2, since 2 is greater than 5 over 4 and within infinity. 12 times 2 minus 15 gives me 24 minus 15, which equals 9. That's a positive number, which tells me that the function is increasing, and that therefore that the slope is also increasing. Now we can move on to part B, which tells us we want to find the direction field graph, or the sketch. So let's set up our coordinate. Now, we need to see what's happening. And I actually don't need to draw this bottom part because our critical point is from 5 over 4, which is a positive number. So let's set this y equal to 5 over 4. Let's say that's this line. And we know that line has a slope of 0 because by setting it equal to 0, we get that critical point, which tells me at 0, or at y equals 5/4, our slope is 0. So now what we need to do is look at our test. What's happening from negative infinity to 5/4, right? So what's happening all down here? Well, we found that the slope is decreasing. So that means that our function must have a decreasing slope at y equals 5/4. So we can just kind of put our arrows down like this, right? Since our slope is decreasing. Right, so that's generally what the section is going to look like. So we're going to have a decrease in slope. Remember, this is just a sketch. This isn't like a real graph. It's just kind of a general way to get an idea of where the slope is and whether we're going towards equilibrium or not. So now we test the last one, which was 5/4 to infinity. We found that the function was increasing, therefore has a positive slope. So that means it's going up like this, right? Our slope is going up. That's what it looks like. So that is our equilibrium solution. So that's part B. Now our last part was to figure out whether this direction field is stable or unstable. Well, this y equals 5/4, this is our equilibrium line, right? This is where the slope is 0. Now, the way you can think about this is because both of these direction fields are going in opposite directions from the equilibrium line, they are moving away from that equilibrium and therefore becoming more unstable. So the answer for part C is that the equilibrium is unstable because both EQ solutions move away from the EQ line or the equilibrium line. So that's the part C answer. So that is generally what you will see for direction fields in calculus 2. It usually does not get very more difficult than this. The only time it might become more difficult is maybe if you were given the original function instead of the derivative function. Like maybe you had to take the derivative first and then plug in numbers. But other than that, this is generally what your professor is going to want you to do. They're going to want you to be able to understand where the slope is increasing and decreasing and how to understand whether it's unstable on both sides of the equilibrium line. Like here, both sides are unstable, right? Both solutions are going away from the equilibrium line. And it's important to be able to identify that. But if you really think about it, you're just doing calculus 1. You're not doing calculus 2 really, because all of this is just calculus 1, right? You're taking very general derivatives. In this one, we didn't even have to take a derivative. We're just using our knowledge from calculus 1 that setting the equation equal to 0 tells me where the slope is 0. What line is that? And then we also get critical points from that. And those critical points tell me the intervals of where the function is increasing and decreasing.